Good afternoon. On a dreary Friday afternoon. Let's say it again. Good afternoon. Okay. So the last time we talked about nutrition and nutritional calories, and the neat thing is that the energy or the change in energy, delta H at constant pressure, that's where we are as human beings at constant pressure, is a state function. So you're taking your food, you're taking fat and glucose, and you breathe in oxygen, so you combust this stuff, to at the end you get CO2 and water, that's what you're breathing out again, and the difference, these are exothermic reactions, the difference you gain in energy, and that's what sustains us. Of course, it's not that simple. If you would have that donut reaction, you put a donut and combust it in liquid oxygen, if this would happen in your body, that would be not very comfortable, okay? Because there is no anti-acid in the world that would be able to counteract that. So there are many, many different cycles and biochemical reactions that occur in your body to get from one state to the final state. There's all kinds of states in between, but that's the nice thing about state functions. We know how much we take in, we know what comes out, the difference is the energy. So we talked about the nutritional calorie, that's the big C, and this is actually in our chemical understanding 1,000 calories, 1,000 or 1 kilocalories. And we then seen that the food people, they like to use the calorie, even if they use the big one, especially it's 1,000, but they like to use the calorie. We are using the joules as the unit, and the joules is 4 times as much than 1 calorie. So the number on the package would be 4 times larger, but you need to remember to convert from calories, and this would be the lower C calories, to joules, you have to multiply it with times 4.18. Okay, and then we talked about the use of energy per time unit. That means it's a watt. 1 watt is exactly 1 joule is burned per second. And this is, when you take these 2,500 FDA recommended calories, and this is the big C, per day, you multiply this by 4, about 4, then you get it in large calories, in joules, I'm sorry, in joules. This is 10,000, and now you have to multiply this by 1,000 in order to get it go from the large calories to the small calories. So this was 10,000, and this is 1,000. So 10 to the 7 joules per day, that's the daily recommended intake. Now, 10 to the 7 joules per day, so the day has about 86,000 seconds, something like this. Let's say 100,000 seconds. So if you divide this, then you have joules per day, cancel joules per second. You get 100 joules per second, and this is 100 watts. So if you sit there just to sustain your basal functions, your basal bodily functions in terms of thinking, in terms of breathing, and just keeping all these iron gradients that make us function in our body, keep them all at the right level, you use about 100 watts per day, all day long. Okay, so, and then we have talked a little bit how much 100 watt is, and then we said, okay, the metabolism is, for example, we store our excess energy as fat. So if you take in more than 2,500 calories per day, or 10 to the 7 joules, and then you store that what the body doesn't need as fat. And in order to get rid of that fat, you have to exercise or eat less, or both. And we have talked how much you burn when you exercise. So 1 pound of fat, it's 9 calories, 9 capital calories per gram. So a gram is 454 grams per pound. You multiply this by 454. So it's about 4,000 capital calories per pound. A pound of fat, okay? So this is if you don't eat for 2 days, you might lose a pound of fat, but you feel lousy, okay? So don't do that. So you might want to eat and exercise, or eat less. And so, of course, there is these typical undergraduate and graduate student diet here. So if you have a Snicker bite, we estimated it's about 50 calories per day. So if to sustain yourself at 100 watt, that means you have 2,500 calories. You eat 50 of those Snicker bites. That's 1 1/4 package I had the last time. That's not a whole lot, no? But there's lots of fat and sugar in there, okay? So, but if you, of course, the other way would, of course, be that you eat 6 donuts about a day. 6 donuts, if you have a little chocolate glaze on, there's a little more. So that's also not a recommended diet because you don't get very much nutrition. So you need to get these calories from vegetables and all the other stuff. And vegetables are very low in calorie, so you can eat mounds of this stuff, and you feel very full. I don't know if you feel satisfied, but that's a different story. Okay? So that was our excursion into human thermochemistry. And today, we want to finish this up. I had asked you that question. So we have here, this is glucose, and we combust this with oxygen. That's what we do. That's what we did with our donut. That's what we do in our bodies. We make CO2 and water, and so we can calculate the enthalpy of reaction of this here. And remember, we had, not the last lecture, but the lecture before, at the end, we had the thermite reaction, where you used that mixture of iron oxide and aluminum, and we ignited this, or we started this reaction. And what you had seen, that the iron oxide plus aluminum makes iron, that was that molten iron that came out of it, plus aluminum oxide. So if you want to calculate now that enthalpy of a reaction, you take the enthalpy of formation of the product, this one, minus the enthalpy of formation of the reactants. That will give you the enthalpy of the reaction, the enthalpy change of the reaction. And I can guarantee you that it would be a negative number, because we've seen all this energy being liberated. That was an exothermic reaction. Now let's look at the energy, the enthalpy of formation for iron. What is that? 0, okay? That's 0. Iron is in natural state. The enthalpy of formation of aluminum oxide is right here, is minus 1676. And the enthalpy of formation of aluminum is what? 0. And the enthalpy of formation of iron oxide is minus 824. So we take this here. This is minus 1676 minus 824. So that is then plus 824. This is something like 852, isn't that right? Minus 852, that would be, if I calculate it right. So that's an exothermic reaction, minus 852 kilojoules per mole, that heat of reaction. And now let's compare this with this one here. We want to calculate this one here. And did I ask you that question? Did we solve this at the end? We didn't solve it. I asked it once or twice? Once, okay. Now I gave you half the answer already. But do you have the heat of enthalpies of formation here? Yes, you do, actually. You can calculate that. Why don't you think about it, discuss it with each other, and give me your answer. This is important that you get this right. So one thing you can say, is it exothermic or endothermic? That's what we did in the last experiment, where we burnt that donut. There was nothing but sugar and fat. Yeah. No, heat is just energy. It's released. Yeah, something moves. Can be rotation. Can be all kinds of things. Yeah, can be rotational energy. Can be translational energy. Okay. You say 1 is bigger than 2, and I agree with you because that's what we sort of discussed already, but you also are smart people. I'm trying to make up for last time. Okay. I did apologize, though. Okay. So we already had discussed this here, so this was not the point here. So this is the point we need to get at this. So the enthalpy of formation of this here is about minus 400 here, is that right? But you have to have it 6 times. And the enthalpy of formation of water is minus 300. You have to have it 6 times. Okay? You add those together. 6 times, what was it? 6 times 400 is 3400 minus. And this is 6 times 300 is 1800, 2400, and 1800 is 4200 minus. Is that right? Minus, minus. Minus 4200. And this one here is 0. And this is, what is it, 1200 minus 4200? It's about 3000, minus 3000 kilojoules per mole. All right, let's see if I did this right in my head here. So that is the heat, the delta H of the change of the enthalpy of reaction standard state is the sum of the enthalpies of formation of these two here, the reactants, plus the sum of the enthalpies of formation of the products. This is 0. There's no stoichiometric number here. So this is then 6 times CO2 is 6 times minus 400. Then we have 6 times water is 6 times minus 300. And 1 time minus 1200. Where is it? Minus 1200. So this is minus gives plus. And with this you are at 3000. Yeah? 3000 kilojoules per mole. If you divide this by 4, then you get it in capital calories. Okay, and you put the molarity in there per gram, so that means it's mostly sugar that was burning. Okay, in this case, it was sugar. We put in glucose to begin with, and all right, so the answer was 1. So today we're going to talk about bond energies, and you all understand now, at least as David Letterman says, or you know who David Letterman is? Okay, good. You know who Greg Ferguson is? Okay, I love Greg Ferguson. Okay, you gotta watch it, tape it. He's at 1:30 at night. Isn't that right? When I can sleep, I watch Greg Ferguson. Okay, now if you don't take anything home, as Letterman and my colleague Kubinick says, take this home from this lecture. Nothing else, but I say that they say this all the time. So if you break bonds, you need energy. Okay, so this is an endothermic reaction, breaking of bonds. Of course, who took AP biology or biochemistry? Who took AP? Some of you have learned, you know that energy is in this adenosine triphosphate bond. That's such an energy-rich bond, is that right? When you break that bond, you get that energy for these other reactions. Who heard that? See how wrong they are. Okay, so the adenosine triphosphate bond, if you break it, you know you need energy. So there can't be energy in there. It's the hydrolysis that's in a reaction with water of this adenosine triphosphate, which then forms adenosine diphosphate. This is what gives you the energy. Okay, you break bonds. It's an energetic bond. It's nonsense. Okay, if you break bonds, you need energy. If you take nothing home, that's what you're going to take home. You might not pass the grade, but this is what you're going to take home. Okay, so you have learned something at least here. All right. So tongue in cheek, we are talking about bond energies, and bond energies are the energy we need to break the bond, but that's a positive energy because we put energy, it's endothermic. But when you form the bond again, it's a negative energy, okay? Because then it's exothermic. That's the energy you gain by forming a bond. So why do we want to learn this? Especially those people who go into bio and chemical biology and molecular chemistry or molecular biology and biochemistry, it used to be called in the old days. You have these huge molecules. Proteins, huge molecules, and that protein changes to another form of the protein, and there's only a reactive center, one reactive center, which is about 5 bonds are changed. The rest of that molecule is not changed. So when you know you break those bonds, if you reform them here in the new molecule, you can calculate that. And these people who work with this, they can estimate by breaking and making bonds if this is an exothermic or an endothermic reaction. Because in order to have these enthalpies of formation tabulated, somebody must have measured it before. So people, they put these compounds together and then let it react and then they measure it in a calorimeter and then they record this and they publish it and it gets published in these tables, okay? These enthalpy of formation tables. But of course, there are so many large molecules. Yeah, nobody has really an interest to measure this enthalpy of formation. So you are doing this week in the lab calorimetry, aren't you? See, now you're well prepared. You're actually parallel the lab and the lecture. So that's how they do it. You use these bond formation and bond breaking approximation. And this is an approximation for many of these molecules, but it's a very good approximation. So you see, these are the enthalpies of formation, and when this is not the bond energies, these are the enthalpy of formation. So in order to come from the standard state, from oxygen, from carbon, that's a solid, that's sort of, carbon is a sheet usually of material and in sheet structures. So you have to break the bonds between the carbons to make it gaseous, to atomize it, and with this you need to put in energy. That's the energy per mole that you have to put in, 717 kilojoules per mole. Oxygen comes as O2 to make single oxygen atoms. You need to put that energy. That's the energy you need to break that bond. So what the bond dissociation energy is essentially what we can do. We have a compound XY. There's our compound XY. This is the energy. Where is the energy state? XY. So we take this, we atomize it. We rip it apart. We break the bond. We know what the energy is. This is our energy. Our new energy. This and this have the new energy. So that's what we needed to put in that energy to break that bond. We get 2 atoms. Okay. Now you can take these 2 atoms and let them form the bond again. So that must be that energy in reverse order. And there you go. So that's negative now. You form that bond again, and you are there. Of course, you had the same energy state because that's what you started out with, and that's what you ended up with. So you break the bonds, and we reform this. I said, yeah. You say, this is quite interesting, but it makes no sense. Why should I break the bonds and then form it? I'm just showing you the principle, okay? And then we will go into some details about this. So these are these bond enthalpies, and they are all positive. So that means when you break them, this is the number that you use, and when you form these bonds, you have to reverse the sign. Because then, if you need that energy to break it, then when you reform the bond or form the bond, that's the energy you gain by forming the bond. So this will have a negative sign. So now let's see, you have a hydrogen. Hydrogen is a unique bond. HH, there's only one hydrogen bond. It's a unique bond. Okay? The bond energy is 436 kilojoules per mole. I have H2. So I break this here. I have 1 mole of H2, and I break this. So I get 2 moles of hydrogen gas, 2 moles of hydrogen atoms. All right? If I do the same thing, hydrogen is a stronger bond, much stronger. This is a weakling here, that bond here. The chlorine-chlorine bond, I can do the same thing. I break that bond. I need 242 kilojoules per mole, and this would be 1 mole. So I make 2 moles chlorine molecules. So now we have broken the bond for hydrogen and for chlorine. So there are hydrogen atoms and chlorine atoms, and now I want to make hydrogen chloride. Okay? So how hydrogen chloride, to make that, to break that bond, it would be 431 kilojoules, but to make it, that I gain, how much energy do I gain? Minus 431 kilojoules per mole. But how many moles of hydrogen and chlorine do I have? I have 2 moles here and 2 moles here, so I need to multiply this by 2 because I'm making 2 moles HCl. So now let's see what this is here. This is about 600 and 676. 676. Okay, this is our reactants. Okay, will be negative. This is our reactants. And what? We want to make hydrogen. We break these bonds. Okay, and then we make these bonds. Yeah. Okay. This here is minus 431 times what? Times 2. That's 862. 862 minus 862 minus. Then we have these other products minus 600 and so that's positive, isn't it right? Yeah. How come it's positive? Okay, that's positive. But this would be exothermic, is that right? Endothermic. It would be endothermic. Minus 831. No. Minus 831. No, this is plus. Minus 862. Minus 862. And this is minus 678. Minus 678. So this is positive. Okay, that would be an endothermic reaction. Okay, all right. So you could say that that's an endothermic. I doubt that I'm making something wrong maybe here, but this is, you get the drift. Okay, we're going to make some examples. Now you look at this here. The oxygen-oxygen bond is 146 kilojoules. It's very, very weak. What kind of a bond is a single bond in oxygen-oxygen? What kind of a bond? Sigma bond. Excellent. So that sigma bond, and this, the double bond would be a sigma and a pi bond. You see, that sigma bond is 146 of 497, and the pi bond is, what is it, 350 about, if you add them both together. Then you get 497. See how much stronger that bond is here? The nitrogen, there are two sigma bonds. See that? There's two pi bonds. I'm sorry. There's one sigma and two pi bonds. There's one sigma and one pi. There's one sigma and two pi bonds. It's 946 kilojoules per mole. Very, very strong bond. You need a lot of energy to break that. However, these carbon-carbon bonds, there is the single carbon, double carbon, it's not quite double, and this is not quite 3 times as much. These bonds here, they are all averages. They are not, because it depends very much on the environment of your carbon-carbon. So there's all kinds of different strengths in carbon-carbon bonds. Of course, they are not big differences, but there is a difference depending on what kind of substituents you have here. Okay, this is a large molecule that can pull on the bond a little bit. And with this, these are average numbers. These are true numbers. Okay, because there's only one chlorine-chlorine or one H bond or one HCl or one nitrogen-nitrogen bond. But these numbers are averages, and so they will give you an approximate number if you use that method. All right, but this method is a good method. So now let's see if we get some tools of this here. You have 1 mole of carbon. Let's see that carbon is sort of a flat structure of solid carbon, and this is our structure here. Okay, it's the cartoon of our structure, and we atomize this. We want to atomize this, and so you need to break all these bonds here. And how many, if you atomize 1 mole of this, how many moles of carbon-carbon bonds do you need to break? 1 mole, 2 mole, or 3 moles? So that atomization means you have, each of them is 1 carbon atom then. So it has to break the bonds, and then it exists as single carbon atoms. So the question is 1, 2, or 3, 1, 2, or 4 bonds you have to break, essentially, to atomize this. You go for the obvious? Okay, you got to think about it. Of course, this will also be an average, okay, an average here, because some of them, you take this here, that would be 4, but not really, okay. Why don't you take one and put one and the next one and the next one, and then draw always the bonds, and think how many bonds you need per atom to draw that. Very surprising result, actually. Very surprising result. You need to discuss this with each other. And so why don't you take one, and then draw the bonds, and then take the next one, and draw the bonds, and then take the next one, and draw the bonds, and think about it this way. Discuss it with each other. That's the average of bonds. And this will give you some further understanding of this. Discuss it with each other. Come on, let's wake up. Such a dreary day, huh? What is it? What is it? Your feeling is probably okay, but why is it? Huh? What is it, you think? You build up that whole grid, okay? You build up that grid. I'll show you. Such a simple thing, and it's so difficult, actually. I totally agree with you. It's very difficult.